All right, today we're going to talk about some antenna operations. This training is not meant to replace hands-on training. It's just going to give you a primer before you actually head out the door and hopefully set you up for success whenever you do head out there to work with the antennas. So our objective is to understand the concepts of antenna ops and be able to correctly point, peak, and pole any SATCOM antenna. First, we'll go over the different antennas that we have. We'll go over some antenna operations research, talk about what you need to do before you head out the door, and then we'll do some practical application. So the different antennas that you'll see out on the pad are a 1.2 meter antenna that is used pretty much exclusively for KA, a 3.7 meter antenna that is capable of CX and KU bands, a 4.5 meter antenna that is capable of CX and KU bands, and then also a UHF antenna. All right, so the steps for peaking and polling are pretty straightforward. The first thing we're going to do is we're going to do some open source research. So we're going to go out on the internet and we're going to look up some information. There are other resources that you have. We're going to stick with open source stuff in this training that anybody can get access to. We're going to figure out what our pointing angles are, and then we're going to find some verification signals so that we can make sure that we're on the correct bird. The next thing we're going to do is we'll set our elevation and we'll search Azimuth. After that, we will verify at least 3 signals. Then we will peak elevation and peak azimuth, and then we will peak our polarization, and we will be done. All right, before you begin, there's a few things you might want to think about. Are you in the downlink footprint? That's good information to know. If you're not in the downlink footprint, you're not going to get anywhere. You're going to waste a whole lot of time if you don't figure that out before you start doing all of the other things that we're going to do. So take some time, check some maps, see where you are, see if there's actually enough signal strength for you to actually use it. Telstar 14R is within our, we are in the downlink footprint. However, it is problematic at times to use it because the signal strength is not quite where we need it to be. Can your system see the signal? So what band is it capable of, and what is it configured to at the moment? If you go out to the 3.7 meter dish and you were looking for a KU signal and you have a C-band LMB on there, you are going to have a tough time. It's going to be a rough day. Also, just because something is in a specific band doesn't necessarily mean that your LMB can look at that frequency. There is KU low, there's KU high. Different LMBs have different frequency ranges, so you want to make sure that LMB can cover or is in the frequency range of the signal that you want to look at. And then obscura. Are there any buildings, hills, anything blocking my antenna's view of the southern sky, or more specifically, wherever the satellite's at? If you have something between you and the bird, you're probably not going to get the signal that you need, and you're not going to get really anywhere. So you're going to want to do your research first. You're going to want to figure out what the azimuth you're going to be pointing at is. You're going to want to figure out what elevation you need to point at. You want to look to see if you can find some beacon frequencies. And you also want to see if you can find at least 3 signals that you can verify with. So the azimuth is just going to be left to right, which way you're pointing. Elevations up and down, which way you're pointing to the satellite. Beacon frequencies. Not all satellites have beacon frequencies that are readily available in the band that you want it to be in, or that you need it to be in, or it could be on a pole that you don't want it to be on. But if you can find one with a beacon frequency on the pole that you're looking for, it makes life a lot easier, especially if the other satellites nearby aren't transmitting that particular beacon frequency. And then the 3 signals. You're just going to want to get the frequency and the bandwidth of each of them so that you can characterize them once you have a satellite tuned in to make sure that you're on the correct one. All right, so your mission is going to be to peak and pole your 3.7 meter antenna on Galaxy 19 horizontal. So we just talked about azimuth, elevation, beacon frequencies, and 3 verification signals, but we're going to go through step by step, and we're going to fill this card out before we even step outside the door. All right. In order to get your azimuth and elevation or pointing angles. Dishpointer.com is a free open source website that you can go to. There's lots of others. Sometimes it's blocked on certain networks. You can still go out. There's apps for your cell phone that you can download. You could look up this information from the front parking lot on your cell phone, and it still would be more than accurate enough for what we're trying to do today. So when you go to this website, you type in first. They're going to ask you to put in your address. It converted my address to lat long, but you put in your address, then you put in your what bird you're trying to look at. Then it'll give you an elevation and a true azimuth and a magnetic azimuth. You are going to use the magnetic azimuth because we're going to be working with a compass outside. If you are working indoors and your particular piece of equipment is aligned to true and it's not using any type of magnetic compass, then you would want to use the true number. The reason that is because with magnetic, we've got a magnetic declination. We're using the Earth's magnetic fields. They're not perfectly aligned to north here in Colorado Springs. So I believe it's the magnetic deck is 8 here. So we will subtract 8 from true, and that's the number that we will use. All right, so now we got the azimuth and elevation filled out. Let's go see if we can find some beacon frequencies. And to do that, I went over to satbeams.com, and I just looked up Galaxy 19 and their list of satellites, and I came up with that they have several beacons here. Unfortunately, they have a horizontal and a vertical C-band beacon, but we are going to be looking to operate in KU today. So unfortunately, the other beacons here don't list whether they're horizontal or vertical, so we're going to have to figure that out as we go. Down here in charts, if you click list, it'll give you a list of frequencies that are open source, publicly updated for TV channels that may or may not still be on there. Like I said, it's all open source and publicly kept records, so it's not exactly 100% correct, but it's pretty close. So a few slides later, when I talk about going to charts and clicking list, that's where you want to go. All right, so now we've thrown our beacon frequencies on there, so we know that this particular satellite should be transmitting these beacon frequencies. That gives us something to try and identify it with. And then also, Dish Pointer is a great resource to find downlink footprints, which you can see here. We are most definitely in the downlink footprint, so we're not going to have any issues there. All right, so this is where I clicked on where it says charts, and I clicked on list. And this is actually one signal right here. Here's the signal going across here. These are all the different TV stations that are all packed into that one signal. But what we want is there's going to be some C-band frequencies that you'll see. We scroll down, we find the KU ones. We're looking for one that is horizontal because that's what we're trying to point at. And what we want is the frequency of that signal, and we want the bandwidth of that signal. So the frequency is 11.842 gigahertz, and the bandwidth of it is 22 megahertz. So we'll write that down, and that's what we'll be looking for. We'll do 2 more of those signals also. So I went on ahead just to save time. I filled out 2 more signals that are available on Galaxy 19 so that we could have 3 to verify with. All right. To save yourself even more time before you step outside, it's good to gather all of the different tools and equipment that you might need in order to peak and pull the antenna. So here is the 3.7 meter tool checklist. What you need, you're going to need a spectrum analyzer, obviously. That particular spectrum analyzer doesn't have to be that one, but it's a mobile one, a handheld that accepts DC voltage, and we use LMBs, so it's ideal for the job. You'll also need either a pocket transit, a compass, or the Sunto that we normally use. You'll also need an elevation tool, unless you're using a Sunto, which already comes with an elevation tool built into it. You'll need a 2-to-1 splitter that will pass DC voltage. Rumor has it we have a few 2-to-1 splitters running around that will pass a signal, but they won't pass voltage, and that makes it very problematic. It can make your life hard for a while until you figure out to swap that out. So make sure that you get the right one. You're also going to need a male-to-male N-type connector and a male-to-male N-type cord, preferably short, but I mean, not too short. You just don't. You want it to be able to reach from where you're connecting in on the antenna to where you can set your spectrum analyzer on the ground. You're going to need a wrench, a 5/16 wrench, 3/4 inch wrench, and a 1/2 inch wrench, and then also a flathead screwdriver. All right, to hook your spectrum analyzer up, there's a few considerations that you need to take into account. The way that our LMBs work is they're powered from the actual system inside, and that system is putting 18 volts over that RF cable that's going into the LMB that's giving the LMB power to do its job. If your spectrum analyzer, not all spectrum analyzers can take DC voltage, but if your spectrum analyzer specifically cannot take DC voltage, you have to hook up a bias T in line with it. And what that bias T does is it'll allow DC to continue through to the LMB, but this other port here, it'll strip the signal off, or it'll allow the signal to come off and strip the DC out so that it won't come into your spectrum analyzer. If you plug a 18 volts DC into a spectrum analyzer that is capable of taking 0 volts DC, you will brick a $30,000 piece of equipment, and it'll be a bad day for everyone. Right here where this red arrow is pointing down, if we could turn that over and look at it directly on, it would tell us whether that port will take any DC voltage or not. The other way that you can hook it up is if you have a spectrum analyzer that is capable of taking DC voltage, you can just hook up a 2-to-1 splitter and you are ready to rock, so long as the voltage coming from the system is not more than the rating that's on that little sticker that's by the port. This one's in particular, it'll take 50 volts DC, and since we're only putting 18 volts on the line, that's well within tolerance. If this system was pumping out 60 volts, we wouldn't be able to hook it up. We'd have to hook up a bias T in line. All right, so we're going to set our elevation first. The reason we're going to set our elevation first is because it's our most accurate number. The elevation is pretty spot on with whatever you got off of the website, right? Whatever we pulled off there, that's close. Your elevation is going to be really close to that. The azimuth's not going to be as accurate of a number because there is going to be some error in that. And we'll talk a little bit more about that in a minute. But all you're doing with the elevation is you're adjusting the antenna up and down in order to get it at the right angle. None of our antennas have offset, so we're not going to go into that. We're just going to skip over that. That can be for a later conversation. So whatever the elevation is, that's what you set the antenna to. Lock it in place, and we're good to go. Some of the elevation tools that you can use. Of course, we have the Sunto on site. It's nice. It does both elevation and azimuth. With the Sunto, you're going to put this wall or this backside of it up against the flat surface on the antenna, on the back of the antenna. And you're going to look through this little port, and it'll tell you how many degrees it is currently facing. There are some of these out and about at some places I've seen where we've had them. These are pretty cool too. This has a magnetic base, and you just take that magnet and stick it to the base on the back of the antenna, and automatically this tells you what degrees you're pointing at. This is a little bit more of a tactical version. It looks like somebody didn't quite have the proper tools, or they didn't go out with the proper tools, so they decided to improvise, adapt, and overcome. You can do this with a protractor. You can do this apparently with a piece of printed off paper and your room key tied to a string. Whatever it takes to get the job done, just get it done. All right, so azimuth. We were talking about there's a little bit more error in azimuth, but azimuth is your right to left adjustment, and the reason that there's more error in azimuth is because your compass is not going to be perfect due to environmental factors. Your compass is measuring the magnetic poles of the earth, but there is rebarb in the concrete. There are big, huge metal dumpsters and trash cans lying around. There are trucks. There's going to be all kinds of things that are going to be in your way that is going to take your compass reading and throw it off a little bit. You want to get as far away from all metal as you possibly can while you're trying to take your compass reading, but practically you're not going to get away from all of it. So your azimuth adjustments not going to be as good. So even whenever you think you've got it pointed directly dead on, you might still have to make some adjustments in order to get it where you need it to be. But with azimuth, you're going to go left to right. You can point from the back of the antenna so long as you have a reference point to where the LMB is on the front, and that will give you, when you do that, you just point at whatever degrees dish pointer told you to, and then you're good to go. You can also do it from the front of the antenna. If you're going to do that, you're still going to point at the LMB, but you are going to invert your number to the opposite of whatever it was, because you're pointing the opposite direction. All right, so Azimuth Tools. Once again, we got the fancy Sunto. That's $225, by the way. And then you can also just use a regular compass or a pocket transit, or there's tons of other tools that can be used to do the same thing. All right. Once you have set your elevation and you've got your azimuth to where you can see signals, you're going to look and try and verify at least 3 signals, whether that's looking at the beacons or whether that's finding 3 of those signals that we pulled off of the SatBeams website and verifying the frequency and the bandwidth in order to make, and those 3 signals are in the right place. If not, it could be that the database is not correct. So if one of those signals is there and the other 2 aren't, you might have to go back in and look for 2 other signals to take a look and see, or you might be able to verify with 2 of the beacons in order to see before you go back in. All right, polarization. In SATCOM, we're always trying to get as much bandwidth as we possibly can out of the asset that's in the sky. In order to do that, we reuse the frequencies because we can linearly polarize half of the signals, and we can vertically polarize the other half. So we can have two signals that are on the same frequency that overlap, but they won't interfere with each other because they're on a different polarization plane. So whenever we polarize our dish, we are going to have to set the skew back and forth to whichever way gets us to that higher signal strength for the pole that we're trying to go for, which in our case was horizontal. So when you're actually trying to really dial in that polarization, get the max signal strength, what you want to do once you've found the beacon, let's say that this beacon is on the horizontal pole, right? What we want to do is we actually want to take the cable off and plug into the vertical LMB, and we want let's say that signal was right here now instead of all the way up here. It's all the way down here. We want to drive that signal all the way into the ground. I didn't mean to click there. We want to drive that signal all the way into the ground until it's just down here in the noise and you can't see it anymore. Then you can flip back over and verify that this signal has actually gotten stronger. It's actually easier to drive this signal. You'll get a better signal strength if you drive this one down into the ground than you will trying to maximize this one. All right. So how do you tell what pole you're on when you're actually physically looking at the LMB or the waveguide? The way you do that is you look at the short side of the waveguide, right? So here's the long side, and this right here is the short side. If you place your finger on top of the short side of the waveguide, whichever way your finger is facing at that moment, which this arrow is simulating, that is the polarization. So this arrow is sitting horizontal, right? This one's sitting vertical. This one's vertically polarized. This one's horizontally polarized. So just real quick, on this particular waveguide here, on the receive waveguide on top, which way do you all think that this is polarized? And if you look here, you can see, if you placed your finger on that short side, it is horizontally polarized. Okay, so that is all that I have for this particular lesson. We're going to go way more into depth when we get out to the antenna. For instance, some other things that we need to cover are how to set up your spectrum analyzer to maximize what you're seeing in your window there. But we'll go over more of that hands-on. It's not really practical to do it via PowerPoint.